third lecture today, and I hope you enjoyed the first session on GAMIT yesterday. So today we are, what we have done is we are which considers the principles, signal structure and data formats. Obviously the literature is pretty available in some of the major good books. We need actually to understand some of the basics. So we'll start. We need to understand the what are the different data formats or you have used. The satellites in the orbit, as we discussed yesterday about the in its orbit, it transmits certain information, and the of information particularly done through a carrier. So it generates certain information, it modulates on, receive those signals for putting the. So we'll discuss this issue today in a little detailed manner, and let's see how we got to know about the positions. So as we know that GPS satellites is, we are using the GPS system for estimating this 3D position, but in addition there is one written term which is written as a receiver time offset. So in this process, what instead of finding the 3D position, we actually estimate this receiver time offset with respect to the GPS time. So time actually follow, in our case of GPS we call it GPS. We know the epochs when he started, the epochs when it changed to understand it. So we'll cover those the concept, what are those GPS time. So when we consider these, so 3D position needs 3 unknowns and one more unknown makes it to 4. So for a unique solution we need to have at least 4 satellites to require for the 4 unknown parameters. So why this receiver time offset comes in your because the satellites and you have atomic clocks, but on the receiver side you have the less. So because atomic clocks are very precise clock and you have certain offset of clocks also from the, but satellites sense those corrections so that you can have that particular offset for those satellite clocks, but for the receiver it doesn't, and you have to estimate it. So in that process we'll see how those corrections can be estimated. So basic steps are nothing but all GPS satellites have synchronized atomic clocks as timekeepers. Second, as we understood yesterday about the broadcast ephemerides, that the coordinate of all satellites are known precisely. So the basic or the fundamental in this GPS is that using those satellites in the orbits as a control point to locate position in the ground. And those who are background surveying, they understood this phenomenon, this principle called triliteration, through which we can use this distance measurement to the known points and we estimate our position. Same principle is applied, but in a we are using the space to Earth. So we also somewhere in the literature we also call it space resection for the similar principle. So these satellites are moving in orbit and they are nothing but the moving control points, and we are using those control points for a position through range measurement. So another point is how those ranges are measured. Satellite coordinates and time signal are transmitted to ground signal. When I say satellite coordinates, so as we should understood that it is not directly the XY on in a particular. Instead, it is a set of coordinates or set of parameters. Rather, I say set of parameters use certain equation, a series of equations to estimate the ECEF XYZ of those satellites. So these signal reach the ground delayed by certain distance traveled. Making use of simple resection principle, and the range information, the satellite and receiver computes its coordinates. So we actually are using the similar principle one by one, and we are estimating our position. So this is nothing but one simple graphical explanation of how your satellites are, you are helping you to find out your position. So as I said that satellites have the onboard atomic clocks. We have the work as an oscillator for them, those satellites, and they generate this fundamental frequency of 10.23 megahertz, and using integer multiplication you generate two carriers which we call it L1 and L2. So the frequency of L1, this is the frequency of L2, they are in the region of ultra high frequency zone. So this is generated by multiplication of 154 and 120. Similar, you cannot use carrier directly for computing the certain position. Instead, satellite also generates certain pseudo random code, which we are sequences at a pseudo random manner. Those we call it codes, or somewhere it is written as gold codes also. It generates uniquely for each satellite. So CA code, which the full form is course acquisition code, P or Y code because it is encrypted form. So P is precise code, and you could see that the CA code is at the chipping rate is 1.023 megahertz. However, for the P code it is 10.23 megahertz. It also sends the navigation message which tells about the satellite itself. Whatever different parameter which we are discussing yesterday when we discussed the orbits, those parameters are properly written in this navigation message. So you need codes, you need navigation message, and at the last, in order to have this level precision in your position estimate, you need those carrier as observable also. So we'll come one by one. What are those prime observables which we are discussing? So we have codes, we have navigation message, we have the carriers also. So as you could see that this portion is empty because CA code is not, because this is a civilian access code, those civilian can access it. So civilian access code is not modulated on L2. So these information are modulated on L1. Simply this information, we call it information because actually this is helpful for us. So this is modulated on L2 and they are properly transmitted by satellites to the receiver. So in a summary form, you would see that all frequencies derive from fundamental frequency F0, which is the oscillator frequency, which is F0 10.23 megahertz, L1, L2, CA code, P code, navigation message. So the chipping rate we understand about in a few slides. What do we mean by chipping rate? So the chipping rate of CA code is 1.023 megahertz. It is that we'll see that what do we mean by this chipping rate, but you could also understand that the wavelength of L1 is 19 centimeter. Just by using this simple equation, you could identify it. In L2 it is 24.4 centimeter. So this is just one simple representation of signal structure. This is the CA code representation. So assuming this 1.023 megahertz frequency for CA code and the repetition rate of 1 millisecond, so that in 1 second you have 1000 repetition, nearly about 1023 repetition of this chip, which we call it binary codes as 010101, and convert it to state. Later on we will see how it is converted respective to 0 to 1 as 1 and minus 1. So this one chip between 0 to 1 is of nearly 1 microsecond. That same could be seen from that 1 millisecond by 1023 chip. So that could be 1 microsecond multiplied by the speed of light. You could say it's 300 meters. So one chip length, which is essentially required, because one chip is essentially required to understand that what resolution you could achieve with this. And the simple thumb rule is available for 1% of chip length is at 3 meters. So we use C code. Theoretically possible is you could achieve this much. But later on we'll see that nowadays with sophisticated algorithm processing we'll achieve more than this. So similar to P code, you could see that the chipping rate is very high here compared to the chipping rate here. It is just 10 times than the previous one, which is is 1.023 megahertz. Here it is 10.23 megahertz. So in the sequence, when 10 come of CA, 10 of 10 combination of Pycode comes. So it is the high chipping rate is that one chip length compared to this 1 microsecond, you have 1/10 of microsecond one chip length compared to 3 meters. And simple one thumb rule is 1% of chip length to allow the signal processing allows resolution up to 30 centimeter. So in the CA code region, we have this two resolution standard, 3 meters and 30 centimeters. Similar to carrier phase also, because it is a very high frequency, so 1575.42, and the one wavelength is 19 centimeter, where compared to the previous one chip, which we call it the shift from 0 to 1 is 1/10th, here it is 19 centimeter. So you could see when we talk about the level precision from the GPS, because yesterday what we are doing, we are processing the SH GAMIT, the models comes up. So with the help of those algorithms behind it, we achieve this much precision in our position estimate. So when we are using carrier phase as observables, not codes, we achieve this much. So again, we were talking about the navigation message. What actually information navigation message carries? So yesterday we discussed about the orbital satellite motion in its orbits. So we discussed about certain parameter, inclination from the equatorial plane, argument of perigee, mean motion, anomalies. So these all are written in a particular manner in those navigation message, and that is also modulated on the carrier too. They also transmit these navigation message to us. So as you could see, this is general information, is that this is a master frame, is consists of 25 frames. One frame consists of 5 subframes, and every subframe consists of 10 words. One word consists of 30 bits. So it is properly segmented. You have complete set of books, and you could say it's transmitted to you, and you one by one page you could have information about different things. In summary, you could call it satellite health, satellite clock information, at what time it was written, at what time it was transmitted, GPS time, GPS week, everything is written in those navigation message, and the receiver is equipped with this algorithm that it needs to read those messages to better understand how to use those information for estimating these satellite coordinates. So please remember, navigation message is the one through which, and using those parameters, you estimate the position of coordinates of the satellites. So length of satellite message is 1500 bits. You could multiply these all and becomes 1500. Modulated on both L1 and L2. Message contains 5 subframes, each of 10 words, each words of 30 bits. So the chipping rate, here we call it the rate at which the information navigation message is modulated on the carrier, is very low, and people call it why it is low, because they have to completely send the information essentially required at the receiver end. So that's why they are very precisely modulated onto the carriers at this rate, and it takes around 12.5 minutes to transmit complete information to the receiver. So the summary is written on that side also, that the master frame, one subframe, one words, and the so-called transmission rate. So each frame start with this 2 word, which we call it, it is written as TLM and HOW, because those who don't understand the navigation message, they need to understand it, what we are reading actually, isn't it, and what we look for. So those two are helping us in achieving this information. But please understand this, the full form of this TLM is nothing but the telemetry word information. It's the standard procedure. You have to understand it one by one. And the second one is HOW, which is nothing but the handover word. So telemetry word contains a synchronization pattern which facilitates access to the navigation message, and the receiver knows it, and then only it will come to know which navigation message actually we are reading. And here, when you could see this word handover is commonly used in day-to-day life also. You have handed over something to someone. So handover word contains the time synchronization information for transfer from CA code to P code. Now please, as I said, CA code is civilian access code and P code is very precise code. So sequence of CA code is allotted to every satellite. Similarly, the P code is also a long code. It is around 260 7 days code, and 1 week of each segment is allotted to a particular satellite. So it repeats after every Saturday midnight, isn't it? So every satellite has its unique CA code as well as its a unique P code also. So, and repetition rate is also given. So every satellite has its own CA code. Every satellite has its own 1 week of P code. It's a long code. Okay. So since P code is precise, and Department of Defense wants that those precise codes can only be accessed to the authorized user, isn't it? So that's why you have to go from that, how to go to P code, because it is 1 week log segment, and if receiver is so slow that it has to track from that start Saturday midnight to every part, it will take so much time. So automatically it helps that where you need to look for that particular segment of that P code. Let's say you are working on Wednesday, isn't it? So Saturday, if your receiver is slow, it has to start from Saturday and then go on to Wednesday. It will take so much time. So this handover word exactly helps us, or helps the receiver to exactly go on to that particular epoch where he has to track for this code, P code. But we need to know, so in the future, in the further slide, we'll also understand that why it has to go to that particular segment. What actually it is requiring, why do we want to go to that particular segment? So we'll come to that part in second few slides also. So that P code can access only after the occurrence of C code supported receiver, time synchronization with GPS time through the Z count. The Z count is another word which we call it is a 1.65 second interval information through which the receiver uses this count information and go down particular second of a particular the P code. So we'll see that also why it is actually needs this information. But in other part after TLM and handover, you could see that it is in a clock correction and SV, satellite vehicle health, ephemeris parameter. Ephemeris parameters are nothing but the orbital parameters which we are actually requiring for estimating the coordinates. Then yesterday we discussed about the almanac also. So almanac is nothing but the information about all other satellites. So when you are tracking satellite number 12, it also gives you that where you look for 1 to 10 and then 13, 1 to 11 and then 13 to 24 satellites. So you have to understand is that one satellite is helping you in every manner so that you have the information about all other satellites. And it also gives you the GPS time information. How do you need to correlate with UTC to GPS time? It also sends the same information. So in summary, your carrier is coming. You could see that if one CA code 1 is coming, the 10th 1010 of P code is coming. So that's how we understand the chip. Okay. Second is how do we modulate those CA code and P code on a single receiver? It has done by the phase quadrature shift of 90 degree. So the code is in a theory term, you could call it code is split in two parts with 90 degree phase quadrature. On one you modulate the CA code, on another you modulate the P code. But before that you modulate the navigation message also on those P code and CA code. So that's how this signal structure comes up. And at the same time you could also understand that this is not a frequency modulation, it is not also the amplitude modulation, it's a phase modulation. So where the chip changes from 1 to 0, the changes in the same pattern of the area you could also observe. It is completely shifted. So this is how the signal is modulated on a carrier and transmitted to receiver. So this is one general summary of those. Why do we need W code? Because WP code is modulo to sum of W code becomes Y code, which is actually we call it PY code. So yes, certain features which we discussed in just one or two segment yesterday is that one of the policy of Department of Defense is that implementation of selective availability. Selective word is somehow missing. It is selective availability and anti-spoofing. So selective availability is nothing tweaking of satellite clock and orbital parameters such that the unauthorized user doesn't get access to actual information. So you could see that if there is certain error in clock, there is certain error in the clock, the estimation of time gets poorer, and because of which the range measurement gets affected eventually. So because of which you cannot, the unauthorized user cannot get the right information in terms of position estimate. So it says cause degradation in position performance by degrading the orbital information, R signal frequency, and in general complicates the solution strategy. So although the DGPS will come to that measurement strategy also later on in the next few slides, maybe tomorrow, that what do we mean by differential GPS, and what we are actually doing in GAMIT is in a layman's sense, we are doing the DGPS work. We'll see that also when we come to measurement strategy. So anti-spoofing is another special feature of this GPS signal, is that P-codes gets encrypted by adding module to some of W code. That's why we have given the summary of W code also, which results in Y code and not relevant for the unauthorized user. It is relevant only for the authorized user. So the potential, as we written in terms of literature, potential enemy might interfere with the US military operations by transmitting a false GPS signal that overrides the real GPS signal. So those who are actually the authorized user, they have this module that we call it SAASM, which is Selective Availability and Anti-Spoofing Module. ASM in a short form. You can also go through Wikipedia also to understand more about it. That module helps it actually to avoid those two. Although a selective availability by year 2000 by presidential order, so we have anti-spoofing available nowadays also. So it is nothing but the encryption, as I said, not possible to geographically selective to implement this anti-spoofing. Please remember that the satellite is orbiting in around the Earth, and it is going places to places, isn't it? Somewhere it is on India, somewhere in the China, somewhere in the Russia. So it cannot apply this the anti-spoofing at a particular geographical location, let's say somewhere about the Iraq or somewhere on the Pakistan, but it has to be thoroughly to everywhere. So that's why it is not geographically selective. CA code, however, would not be affected. It is only for P code. So very expensive civilian P code receivers available. When we talk about the geodetic or dual frequency receivers, they have this kind of facility. They are very expensive. So manufacturers have developed proprietary receiver software combination. I am talking about the module that can see through this encryption. They can know that what is actually W code, so that we can get to the P code, actual P code. So the military has exclusive access to PY code receiver, which included direct reception capability. So now we understand that GPS, in the GPS signals which is coming from the satellites, we are actually using certain information which is modulated onto those carriers. One is codes, the gold codes, second are those carriers, isn't it? So similarly, based on these two observables, which is nothing but the pseudo ranging, we'll come to that. What do we mean by pseudo ranging? We are using those codes and carrier phase measurements, and we are using those two techniques for measuring our position. So we'll see that also. But before that, as I was saying, why do we need to understand this pseudo ranging? Why does pseudo ranging comes, isn't it? So it is because that we are actually using those codes which are coming from the satellite, and receiver is generating a replica of those code so that it can align accordingly to estimate the time shift, which we call it time delay in the travel of those signals. The moment it gets locked to that particular satellite, it starts immediately this code correlation phenomena. So correlating the two codes, one which is coming from the satellite, one itself it is generating. We call it replica of those. So those from the electronics background, they understand is much better that the code correlation phenomena is working on. So with the help of those code correlation phenomena, we actually estimate this delta t, which is nothing but the time travel, to estimate that this much time has taken the signals to reach the receiver. So with the help of this delta t, we can estimate the range, but here we call it pseudo word. There is a word which is called it pseudo range, isn't it? So the pseudo word comes for the fact that your receiver clock is not much precise as compared to the atomic clocks, as well as there are certain errors in between that signal path, isn't it? So because of this, we don't get the real delta t, instead we get a different delta t that has certain errors. So that's why when we multiply it by the speed of the waves or the carriers, we get different range altogether. So that's we call it pseudo range. So how do we get this delta t? The code correlation phenomena. It's aligning the incoming signal with the replica of this. So the correlators generate so many replicas. So but they generate early, they prompt, and they very late. So with the help of these early, late and prompt phenomena, we generate this maximum peak. So if the code is properly aligned with the replica, we'll get the maximum peak. This is nothing but the summation of the products of individuals. So this is the replica, -1 multiplied by 1, 1 plus 1, 1. So similarly for 10 codes, 1 0 1 0 1 0 will get, please remember this is the states, not the x 1 0. It is a state which is converted. For 0 state is 1, for 1 state is -1. So that's why we get a the code correlation is equal to 1, which gets the peak. So we get the peak when the correlation is actually happened. There is another word which we call it cross correlation. So generally signals, the codes are prepared in such a manner that when you actually cross correlate it, you get less peak every time, isn't it? So these are the basic background on how do you estimate that delta t, isn't it? Similarly, this is the one modulations which we actually discussed, that signals, the codes are modulated onto to the carrier, that intentionally increasing its bandwidth so that it becomes resistant to jamming also. So that is spectrum, which we, this is another detailed discussion on how we are getting on the P-code as a increased bandwidth of 20 megahertz, and of C-code we have only 2 megahertz, and of navigation message we have only 100 hertz. So this is a detailed discussion on how the modulation is being done, what do you mean by spectrum, but it is the backbone of the signal structure at the GPS satellite side. So as we said, we have this delta t information. This is the complete equation is written of the code pseudo ranges, both for CA code as well as for P code. So this P is nothing but the pseudo range measurement. You could see, just ignore for the time being these all the right hand parts of these, from D ion, D tropo, multipath, and then the combined receiver clock error. So what we are doing, we are understanding only this part at a time. So this is delta t. Let's say if you are assuming that has been given by the after code correlation, you got delta t. So this delta t multiplied by C becomes pseudo range, but it has actual shift from that true geometric range. We need to understand this part also, because you have to use this true range, but it is not available to you. So you are working with the code pseudo ranges, but apart from these clock errors, which we call it receiver clock error as well as the satellite clock error, but the navigation message, the clock correction parameter, will come to that part also. What are those clock correction parameters? But we'll use those clock correction parameter to estimate of the satellite clock, so that only error becomes is the so-called offset from the GPS time of the receiver clock. So that pseudo range measurement, the true range, orbital errors, speed of light, satellite clock offset from GPS time, receiver clock offset from GPS time. So I'm talking about that this dt is available, so you can estimate it. Similarly, this true geometric range is nothing but the actual x of satellite, actual y of satellite, z of satellite in ECF system. Similarly, the phase observable, which are actually helping us to achieve the level precision, the similar equations can be written. But please remember, we'll come when we are discussing the error budget, we'll see that why this plus sign comes up in the code pseudo ranges and why this minus sign comes up in the carrier phase observable. So we'll discuss then we are discussing the error budgets. But here we have a next slide which tells you about the problem with the carrier phase measurement. Is that when you lock onto the satellites, you don't know how much cycles has been missing previously before from the satellite to the moment you get locked. So what will happen is that at this moment you don't know the actual integer ambiguities. Instead, the moment you get locked, you are actually looking at some fraction of that cycle, and you lock onto that moment, and you start in memory you writing those numbers from that particular moment. So fractional phase at epoch this ti, then integer full cycle since that particular moment of lock, and this initial ambiguity which are actually unknown. So one of the major segment of carrier phase processing is that ambiguity resolution. You have to resolve those ambiguities, and in fact in the last session of GAMIT there is a written word called WLNL. That will come to later on, that what do you mean by wide lane and what do you mean by narrow lane. That is nothing but the combination of L1 and L2, so that you'll achieve this ambiguity fix. Another cycle slip that Professor Herring was discussing about the cleaning of your data set, isn't it? you have to make sure that you don't have any cycle slip in your data set. So cycle slip is nothing but having another offset in your data set, so that when your receiver gets off and the moment it's another time it's locked onto the satellite, that n value is changed. So previously you are locked, you have this much measurements up to this point, and then you have something happens to your receiver, another time you get locked on, you'll have another offset in terms of this value. That becomes the integer ambiguity shift. So this is cycle slip, which you don't want in your data set. You generally want your data set to be perfectly. So there are ways to detect these cycle slips also, and nothing but you have to use those combinations, and we'll see in later on few slides that what are those combinations or what are those observables which are actually helping us to realize that my data set has those cycle slips or not. So as I said, this is just a similar representation of what we have discussed in the summary section. CA code is 10 times slower than P code. Similarly, whatever it is written about the L1 and L2, similarly 19 centimeter, 24 centimeter, and how these helping in achieving the MM level. So this is the comparison of the observable. In code, please remember, ambiguity terms doesn't come. It only comes in the carrier phase measurements. So these are the GPS formats, some important formats. We are actually using in our GAMIT session, we are using the rhynocs files of the stations, of our local station, which are also used together with the IGS rhynocs files for the processing. So rhynocs, as I said, it is now, as we know that this discussion on the first day, now version 3.00 onwards are also available, and many times you would see that rhynocs file of 2.00 of the previous data set. So rhynocs most recent version is rhynocs 3.03 from July 2015, and nowadays because of the satellite constellation from other countries are also available, so the rhynocs file is huge in terms of not only GPS pseudo range or carrier phase measurements are available, but instead from GLONASS also you have data set, isn't it? So from Galileo also you have data set. So because of these, they are changing the formats. So rhynocs contains 3 files. When you open the zip file of any rhynocs data, you have observation file, you have navigation message file, and you have meteorological data. Generally the above 2 we are using, isn't it? So in the GAMIT folder you should check what type of folders you are actually creating. One is rhynocs, one is BRDC, another is IGS. So you should understand also that what rhynocs folder contains, what BRDC folder contains, what the IGS folder contains, so that you could understand what products you are using. So the data set also, you should also not only just copying the rhynocs file which is given to you, also understand what type of its format we are using. So it is written in terms of the 4-character name for the station, similarly the information about the day of the year, and then this F belongs to file sequence number, daily file. If it is a 24 hours data, you'll have a 0 written over it. Then the YY, which is nothing but again helps the 2-digit year, and this T helps you understand whether it is a rhynocs observation file, it is a navigation message file, it is observation, it is a meteorological file, or you have access to GLONASS also, you have access to Galileo also. So it is a wide information. But the content on rhynocs is available huge on internet. You should read if you want to read from the IGS data sites. So you can go to IGS sites. You can understand these formats very well. Similarly, when you open your rhynocs file in any maybe you could see this upper segment which we call it header file, the rhynocs, and here actually the data set which we are using. So this you could see this version is 2.10. So in the next slides the header is explained, so that one by one it is written as this PGM run by date. So it is nothing but program, agency, date of creating the file. On the next line is marker name. So receiver number, type, version, similarly antenna type, number. So that information actually you were using when you are writing the station info file. So sir was creating a directory so that you could properly enter what file, what antenna you are using, because if you enter the wrong antenna, you may stuck in during the GAMIT processing. So everything is written, the 4 observable, C1, L1, P2, L2. The moment when you use this word P2, C1, it means that we are talking about CA code modulated on L1, that becomes CA. C1. P1 is nothing but the P-code modulated on L1, that becomes P1, and L2 is nothing but the second carrier wave which we are using. So this is this general explanation. The moment you try to see this and when you try to relate it, it's very easy to understand. It also gives you time of first observation, number of observation times, etc. So as I said, pseudo ranging using CA code on L1, phase measurement on L1, P2 is pseudo ranging using P code on L2, phase measurement on L2. This is the observation file. You could see that it is the epoch, event flag, number of satellites from that G word is written, isn't it? G, 2G, 6G, 7G, 8G. So these are the satellite numbers which you are actually computing this pseudo ranging. So an observation data for each satellite. These are nothing but the observation data for particular satellite, and for first, if it is written 10G, so this is information about 10th satellite. The second one is second satellite, 6th satellite, 7th satellite, and so on. And this is one segment which we have taken. This is the C1, the pseudo range measurement on C1, phase measurement on L1, P2 and L2. You could see that there is this indicator is loss of lock indicator. So if you have nothing, blank, which we don't know, if it is written 0, it is okay. If it is written 1, cycle slip has occurred. So every information which is ever required, just by looking at the rhynocs file, it is available to you. Signal strength is also coming. So minimum possible signal strength and the maximum possible signal strength. Another one is the navigation data. Although you are not using navigation data directly in terms of computing the coordinates, because in the background it is already written. So this is again with the parameters which we discussed in the first lecture, is that the mean motion, semi-major exit, right ascension of the ascending node. So these all information are properly written for every orbit. So these are the PRN date, time of clock. These are the three wonderful parameters which actually we studied, A0, A1 and A2, which are not, it's helping us to understand the clock behavior, to actually estimate the drift of the clock, isn't it, from the GPS time. So GPS satellites actually sending their own correction parameter, and they you have to use those correction parameter to find the estimate of. So every time when we write the equation, we already say that okay, clock correction from the satellite end is known. So how it is known? Because it is already provided. So this is the PRN, T0. We are using, this is another detailed explanation on how you are using this clock parameter to estimate those corrections for the satellite clock. You are using this A0, A1 and A2 for estimating those clock corrections. Another international efforts who are helping us from those as an international body, so that we have our position as in a precise manner. So one agency which is nothing but International GNSS Service, which we actually call it IGS, that is the folder you are creating because you are using those products. So formerly the International GPS Service, because previously GPS was popularly used, now we call it International GNSS Service, is a voluntary federation of more than 200 worldwide agency that pool resources for GPS and GLONASS station data to generate the precise GPS and GLONASS product. Because if you are not capable of writing those codes, they are developing the products which you can directly use. So that nowadays when you heard what precise point positioning or triple P, so the triple P is possible because of products which are available from those international agencies. So obviously you are using those products for earth science research, multidisciplinary application and education. So these are the centers. The another efforts is one of the other efforts is International Earth Rotation Service, which is actually helping with the frames which I was talking about yesterday, is the ITRF and ICRF. Those are the agency which is helping us to get prepared with the updated information about those frames. So these are the missions through following technical centers, product center, combination center, analysis coordinator, center bureau and directing board. These are the organization board, and Professor Herring is analysis coordinator of this of the IRIS directing board. Now also know that what type of receivers, the data file which you are getting for IIT Kanpur is that rhynocs file which you are getting. What type of receiver it could be, because GPS has different type of receiver altogether, your watch, your mobile phone, the high quality receiver, the very expensive receiver. So classification of receiver has also been done in a different segment. Code phase receivers, carrier phase receivers. So in carrier phase, or those receivers which only have access to CA code, those receivers will have to CA code as well as P code. Some codeless receivers also there. So this is a complete vast domain of understanding. But what we are actually relevant is that we should have understanding about what do we mean by single frequency receiver and what do we mean by dual frequency receiver. And what is the importance of having this dual frequency receiver is that you actually combine the either remove or reduce the ionospheric error which is coming to you. So we'll understand also this, that the main observable is the code pseudo ranges, the carrier phase observable, as well as the importance of dual frequency receiver. So the explanation of types of receivers can be done in a variety of manners. But the importance is because we are actually doing the rhynocs, the GAMIT processing on the rhynocs file, which is of the geotic quality receiver, which is very precise receivers. The characteristics are, the both frequencies should be available. It should track both all possible satellite constellation, GPS, GLONASS, Galileo, full wavelength on L2 and AS62, low phase and code noise, high data rates. Data rate should be high for kinematic application. You cannot have 1 hertz data rate for a kinematic application. Nowadays, this is also increasing, but the cost is also increasing. High memory capacity, full operation capability, multipath mitigation, good onboard and office software. So these are some of the qualities of geotic receiver. But please remember, this is the receiver which we don't have access to in our day-to-day life. We don't work with the geotic quality receivers, isn't it? So summary of steps, what we actually need when we go for signal processing is that splitting of incoming signal into multiple satellite signal, generation of reference carrier or replica, generation of reference PRN code, acquisition of satellite signal, tracking of code and carrier, demodulation. So these are the steps are actually followed when at the receiver end, when the signal just arrive at the receiver. So that's how we estimate. And steps 1, using satellite ranging, you get the pseudo ranging information, carrier phase observable, get perfect timing. When I say perfect timing, is that means that delta T should be precise in terms of satellite clock estimates. So, and these are the errors which will, on one lecture, will cover all those errors. What do we mean by ionospheric error, how it is affecting, what do we mean by tropospheric error, geometric dilution of precision, what do we mean by dilution of precision, where do you see this value of DOP value, which we normally call it, what is the importance of this DOP value. Thank you. Thank you. Time it down. Yes.
So, hello. Between this GPS is basically